What if everything in the universe, every swirling galaxy, every spiral shell, even the way leaves grow on a stem, followed a secret code? Picture this. The same mathematical pattern that shapes a seashell also appears in the arms of distant galaxies. It's called the Fibonacci sequence, a string of numbers where each one is the sum of the two before it. 1, 1, 2, 3, 5, 8, on and on, revealing itself in the unlikeliest places. This isn't just coincidence, it's a whisper of something deeper, a hidden order woven into the fabric of reality itself. And today, we're going to unravel 30 of the most astonishing theories about these cosmic patterns, ideas that will make you question whether the universe is random or if it's all part of a grand, mysterious design. Think about the last time you looked up at the night sky. Those stars aren't just scattered randomly. Some scientists believe they're arranged in ways that mirror the branching of neurons in our brains, as if the universe and the human mind share the same blueprint. Or consider the golden ratio, a number so precise it appears in the curves of hurricanes, the proportions of famous artworks, even the structure of DNA. Why does nature keep returning to these shapes, these numbers? Is it simply efficiency, or is there something far more profound at work? From the way black holes align to the eerie synchrony of celestial events, these patterns hint at a universe that's anything but chaotic. So what's really going on? Over the next while, we'll dive into theories that range from the mind bending to the spine tingling. Could our universe be a simulation with these patterns acting as glitches in the code? Or are we seeing the fingerprints of a higher dimensional reality bleeding into our own? Some researchers even propose that the cosmos operates like a cosmic computer, processing information through these recurring designs. Whatever the truth may be, one thing's certain: the deeper we look, the more the universe seems to whisper its secrets, if only we know how to listen. Ready to uncover them? Let's begin. Take a sunflower's face, look closely, and you'll see its seeds swirl outward in perfect spirals, some curving left, some right, but always in numbers that match the Fibonacci sequence: 5, 8, 13. Now zoom out to a galaxy like the whirlpool, and you'll find those same spirals etched across cosmic scales. This isn't just nature's flair for artistry. It's efficiency written into the laws of existence. The Fibonacci sequence, where each number is the sum of the two before it, shows up in the tight coils of nautilus shells, the branching of trees, even the way rabbit populations grow. And when you map these patterns, something eerie emerges. They all dance around the golden ratio, roughly 1.618, a number so precise it's been called the universe's signature. Renowned astrophysicist Dr. Mario Livio spent decades unraveling this mystery. His work reveals how the golden ratio appears in the spin of distant galaxies, the turbulence of storms, even the twists of our own DNA. But here's where it gets controversial. Some scientists argue these patterns are inevitable, just the most efficient way for energy and matter to organize. Picture a waterfall. The water doesn't choose the fastest path downward, but gravity shapes its flow into curves that minimize resistance. In the same way, Fibonacci spirals might simply be nature's path of least resistance. Others, though, see something deeper. They point to quantum physics, where particles flicker in and out of existence in patterns that eerily echo Fibonacci numbers. Could this sequence be woven into the quantum fabric of spacetime itself? Ancient architects certainly thought so. The Parthenon's columns, the pyramids of Giza, even Da Vinci's Vitruvian Man all lean on the golden ratio for balance and beauty. But the most tantalizing idea, that these patterns are clues to a universe built on mathematical harmony, where everything from atoms to galaxies follows a hidden rhythm. So is it coincidence or cosmic law? The debate rages on. But one thing's clear: whether by chance or design, the Fibonacci sequence is a thread stitching together the tapestry of reality from the infinitesimal to the infinite. But what if these patterns reach even further beyond galaxies and sunflowers, etched into the very afterglow of creation itself? The cosmic microwave background, or CMB, is often called the universe's baby picture, a faint glow left over from the Big Bang stretching across the entire sky. Yet when scientists mapped its subtle temperature variations, they stumbled on something unsettling. Instead of randomness, they found eerie alignments, a so-called axis of evil, where hot and cold spots line up in ways that defy conventional cosmology. Dr. Kate Land and her team at Oxford first flagged this anomaly. Their analysis revealed large-scale patterns in the CMB that seemed to point in a specific direction, as if the early universe had a preferred orientation. This shouldn't happen. The standard Big Bang model assumes the cosmos is isotropic, meaning it looks the same in all directions. But if the CMB holds a hidden axis, it throws that assumption into chaos. Some theorists suggest it could be evidence of a pre-Big Bang structure, like wrinkles in space-time from a previous cosmic cycle. Others propose something even wilder, that our universe is fundamentally lopsided, with physics itself varying depending on which way you look. Here's why it's controversial. Mainstream cosmology relies on the idea of a smooth, uniform early universe. The axis of evil challenges that, hinting at forces or conditions we don't yet understand. Critics argue it could just be statistical noise, a fluke in the data. But if it's real, the implications are staggering. Imagine space-time having a grain like wood, with events unfolding differently along its hidden lines. Ancient light might carry clues not just to our universe's birth, but to something beyond it, a shadow of whatever came before. So is the CMB whispering secrets from before time began, or is this just another cosmic illusion? Either way, it's a reminder that the universe still holds mysteries no equation has yet cracked, and that sometimes the most profound truths hide in the quietest echoes of the past. Now imagine a set of numbers so strange, even mathematicians call them the crazy relatives in the attic of algebra. Meet the octonions, an 8-dimensional number system where multiplication isn't just tricky, it actively defies common sense. Unlike ordinary numbers that follow neat rules, octonions twist and flip in ways that make them nearly impossible to visualize. Yet some physicists believe this mathematical oddity might be the secret language of the universe, written into the very particles that make up reality. String theorist Cole Fury has spent years piecing together a radical idea that octonions could be the hidden scaffolding behind quantum mechanics. Here's why that's revolutionary. The Standard Model, our best blueprint for particle physics, describes a zoo of subatomic particles from quarks to electrons, each with quirky properties like spin and charge. But the model's messy, patched together with constants that feel arbitrary. Fury's work suggests octonions might clean up the chaos. When she maps known particles onto octonion math, their behaviors snap into place like puzzle pieces. Suddenly, abstract concepts like why matter has 3 generations, or how particles choose their quantum states gain a chilling elegance. Critics argue this is speculative, but the clues are hard to ignore. Octonions naturally replicate symmetries found in the Standard Model, hinting at a deeper unity. Picture it like discovering all languages stem from one ancestral tongue. Even stranger, the number 8 keeps surfacing in physics, from the 8 gluons binding atomic nuclei to the 8-fold way of organizing quarks. It's as if reality has an octonion-shaped skeleton. So why haven't we cracked the code yet? Octonions are notoriously unstable. Tiny errors cascade wildly, making calculations nightmarish. Some compare it to building a house on a trampoline. Yet if Fury's right, we might be staring at reality's source code, a mathematical structure so profound it could rewrite how we see everything from black holes to the birth of time. Whether a dead end or a breakthrough, one thing's certain: the universe's deepest truths often wear the most unexpected disguises. Imagine floating alone in an endless void, no stars, no planets, just darkness stretching forever. Then, out of nowhere, a flicker of energy twists itself into a single, self-aware thought. No body, no memories, just a brain conjured from pure chaos. This isn't science fiction, it's the Boltzmann brain paradox, one of the most unsettling ideas in cosmology. The paradox starts with a simple question. If the universe tends toward disorder over time, why does it contain islands of order, like galaxies, planets, or you? Austrian physicist Ludwig Boltzmann first proposed that random fluctuations in entropy could temporarily create complexity, even consciousness, in an otherwise lifeless cosmos. But here's where it gets eerie. If the universe lasts long enough, trillions upon trillions of years, these fluctuations could spawn entire minds from the void. A Boltzmann brain would be a self-aware entity, convinced it's living in a real world, complete with fake memories of a past that never existed, and statistically, it's more likely you are one of these random flickers than an actual human in a stable universe. Max Tegmark, the MIT physicist known for his multiverse theories, takes this even further. In a cosmos with infinite parallel realities, Boltzmann brains might outnumber ordinary observers, making it probable that most conscious experiences are just fleeting illusions. Critics argue this is philosophy dressed as physics. They point out that if Boltzmann brains dominate, science itself becomes unreliable after all. How could a random fluctuation trust its own observations? Yet the paradox lingers because it exposes a crack in our understanding of time, entropy, and reality's fabric. Some theorists propose escape clauses. Maybe the universe will eventually collapse before Boltzmann brains can dominate, or perhaps consciousness requires more than just random neuron-like flickers. Either way, the paradox forces us to confront a haunting possibility. What if reality isn't the steady, ordered stage we assume? What if our most cherished memories, even this very moment, are just sparks in the dark, destined to dissolve as quickly as they formed? The universe might not need permanence to create meaning, but that doesn't make the question any less dizzying. What if everything you see around you, the trees, the stars, even your own hands, isn't really three-dimensional at all? Leonard Susskind, one of the fathers of string theory, proposed a mind-bending idea called the holographic principle. It suggests our universe might be a two-dimensional surface, like a cosmic movie screen, projecting the illusion of depth. Think of it like a credit card hologram, flat but shimmering with the appearance of three dimensions. The real kicker: this isn't just philosophy. Black holes might hold the proof. When matter falls into a black hole, it doesn't just vanish. According to the laws of physics, information like the spin of particles or their quantum states can't be destroyed. Susskind and Dutch physicist Gerard T. Hooft realized something startling. The information swallowed by a black hole doesn't disappear into the singularity. Instead, it gets smeared across the event horizon, the point of no return, like data encoded on a scratchy vinyl record. The event horizon is a two-dimensional surface, yet it somehow stores all the information needed to reconstruct the three-dimensional objects that fell in. This discovery led to a radical conclusion. If a black hole's interior can be fully described by information on its surface, maybe the entire universe works the same way. In 2017, Fermilab took this idea from theory to test. Their holometer experiment fired lasers down two perpendicular 40-meter tunnels, searching for minuscule vibrations in spacetime. If the universe is truly a hologram, they reasoned, there should be a faint pixelation at the tiniest scales, like static on an old TV screen. While the results weren't conclusive, the experiment opened a door. Future research could detect these spacetime glitches, proving we're all living inside a cosmic projection. Skeptics argue this is speculative, but the math holds up. Even gravity, the force we think of as sculpting the cosmos, might emerge from interactions on that hidden two-dimensional surface, like how the pixels on your phone create the illusion of movement. If Suskind's right, reality isn't just stranger than we imagine, it's stranger than we can imagine, and somewhere written on the edge of the universe there might be a line of code with your name on it. What if the universe around us, the stars, the laws of physics, even the sensation of wind on your skin isn't real? Oxford philosopher Nick Bostrom laid out a chilling argument known as the simulation hypothesis, framed as a trilemma with three unsettling possibilities. Either civilizations like ours almost always go extinct before reaching technological maturity, or advanced civilizations lose interest in creating simulations of their ancestors, or we're almost certainly living inside one right now. Bostrom's logic is relentless. If future humans could run ancestor simulations with conscious, self-aware beings inside them, and if they chose to do so, the number of simulated minds would vastly outnumber biological ones. Statistically, the odds tilt overwhelmingly toward us being artificial constructs rather than flesh and blood originals. The idea gains traction when you examine the universe's quirks. Take the Planck length, the smallest possible unit of space. It's as if reality has a pixel size, a fundamental limit below which measurements become meaningless. Could this be the resolution of our cosmic simulation, the smallest bit the system can render? Then there's quantum mechanics, where particles exist in fuzzy superpositions until observed, like a video game that only loads detailed graphics when a player looks directly at them. Physicist Silas Bean even suggested that if we're in a simulation, high-energy cosmic rays might reveal a subtle grid-like structure to spacetime, like artifacts in a poorly rendered digital image. Elon Musk famously declared the odds we're not in a simulation are 1 in billions, arguing that 40 years of gaming evolution, from Pong to photorealistic virtual reality, suggest future simulations will be indistinguishable from base reality. But skeptics push back. They ask, why would any civilization waste cosmic-scale computing power simulating ordinary lives like ours, unless, of course, we're some researcher's anthropology project or a forgotten server running in the background of a post-human world? The simulation hypothesis forces a jarring question. If reality is code, who or what wrote it? And more unsettling still, if the simulators ever pull the plug, would we even notice? We know crystals for their repeating patterns in space. Think of snowflakes or diamonds, where atoms arrange themselves in perfect, three-dimensional symmetry. But what if crystals could also repeat in time? Nobel Prize-winning physicist Frank Wilczek first proposed this wild idea: time crystals, structures that oscillate endlessly without energy input, breaking one of physics' oldest taboos, perpetual motion. Unlike ordinary matter, time crystals don't settle into equilibrium. Instead, they pulse in a loop like a clock that ticks forever without batteries, their atoms returning to the same arrangement at regular intervals. It sounds impossible, but in 2017, scientists at Harvard and the University of Maryland created microscopic versions in the lab, using lasers and chains of ions to force matter into this strange time-looped state. Wilczek's original vision was even grander. He imagined time crystals spanning cosmic scales, woven into the fabric of spacetime itself. Picture the universe as a tapestry where not just matter, but time has a crystalline structure, regions where the flow of moments repeats like the grooves in a vinyl record. These four-dimensional crystals wouldn't just exist in spacetime, they might shape it, influencing how gravity bends or galaxies spin. Some theorists suggest they could even explain dark matter, with invisible time crystal halos twisting gravity around galaxies in ways we don't yet understand. Critics argue time crystals can't do anything useful. Their motion is locked like a pendulum, forever swinging the same way. But supporters counter that even locked rhythms can store information. A universe laced with time crystals might function like a cosmic hard drive, with data encoded in the very pulses of reality. And here's the real twist: if time crystals exist naturally, they'd be the first objects to break time translation symmetry, meaning the laws of physics would look different at different moments inside them. That's as radical as finding a place where gravity suddenly repels instead of attracts. Could time crystals be humming beneath our feet, tuning the universe's deepest rhythms? We've only just begun to listen, and if Wilczek's right, the cosmos might be far more rhythmic and far stranger than we ever dreamed. Deep in the cosmos, something strange is pulling. Not gravity as we know it, not the tug of nearby galaxies or the whisper of dark matter. This is something bigger, something beyond. In 2008, a team led by NASA astrophysicist Alexander Kashlinsky made a discovery that sent shockwaves through cosmology. They found hundreds of galaxy clusters, each containing thousands of galaxies, all streaming in the same direction at breakneck speeds, as if drawn by an invisible hand. They called it the dark flow. Here's what makes it eerie. These clusters aren't just moving randomly, they're racing toward a single point in space beyond the edge of what we can observe. The sheer scale defies explanation. We're talking about motion spanning billions of light years, far too vast to be caused by any known structure in the universe. Kashlinsky's team used the cosmic microwave background as a measuring stick, tracking how the cluster's motion distorted this ancient light. The result: a velocity of nearly 2 million miles per hour toward something we can't see. So what could be out there? One theory suggests a massive superstructure from a time before the Big Bang, a relic of another universe that left its imprint on ours. Picture it like a footprint in wet concrete, an echo of something colossal pressing into the fabric of reality. Others propose a gravitational tug from a neighboring universe in the multiverse, a place where the laws of physics might be entirely alien. The most unsettling possibility, that dark flow hints at a fundamental flaw in our understanding of spacetime itself, a crack in the cosmic egg. Critics argue it could be a measurement error, a trick of the data. But Kashlinsky's findings have held up under scrutiny, even as newer studies confirm the anomaly. If the dark flow is real, it rewrites the rules. It means the universe isn't just expanding, it's being pulled. And whatever's doing the pulling doesn't play by the physics we know. So is it a phantom, a sign of something deeper, or just the universe reminding us that no matter how much we learn, the unknown always looms larger? One thing's certain, out there in the black, something is calling, and we've only just begun to listen. What if the Big Bang wasn't the beginning, but the echo of something far stranger? Picture a black hole so massive, its gravity warps not just space, but reality itself. Now imagine that inside that abyss, a new universe is born. This isn't science fiction. Polish physicist Nikodem Poplawski proposed a radical twist on cosmic origins, that our entire universe might exist inside a higher dimensional black hole, with the Big Bang marking the moment matter and energy spilled into this hidden realm. The idea hinges on a peculiar property of black holes, their singularities. Under general relativity, a singularity is a point of infinite density where physics breaks down. But Poplawski's models introduce torsion, a twist in spacetime that prevents true infinities. Instead of collapsing endlessly, matter rebounding from this torsion could trigger an outward explosion, a big bang from the inside of a black hole's shadow. Think of it like a cosmic Russian doll, our universe nestled within a parent black hole, which itself might reside inside an even grander cosmos. Evidence. Look no further than dark matter. Poplawski's math suggests the torsion field from the parent black hole could manifest in our universe as an invisible force mimicking the gravitational effects we attribute to dark matter. Even stranger, this model predicts our universe has a preferred direction, a relic of the black hole's original spin. And here's the kicker. Some observations of distant quasars show their jets aligning mysteriously across billions of light years, as if space itself has a subtle grain. Critics argue this is speculative, but the elegance is hard to ignore. If true, every black hole in our universe could harbor its own cosmos, a fractal infinity of nested realities. The implications are dizzying. Did our universe inherit its physical constants from the black hole that birthed it? Could we ever detect their outside? For now, these questions linger at the edge of known physics, but one thing's certain: if Poplawski is right, the cosmos isn't just stranger than we imagined. It's a story written in the ink of singularity. Imagine you're watching a spinning coin at first. It's a blur of possibilities, neither heads nor tails. But the moment it lands, reality seems to snap into focus. Quantum mechanics says particles exist in this same fuzzy state until measured, a paradox that's baffled scientists for decades. Enter Wojciech's quantum Darwinism, a theory that doesn't just solve the puzzle, it rewrites how we think reality forms. Wojciech's idea starts with a radical shift. What if the universe itself is constantly measuring quantum systems, not with lab equipment but through entanglement? Every particle interacts with its environment, collisions with air molecules, whispers of radiation, even the faint tug of distant stars. These interactions create countless copies of stable quantum states, like ripples spreading in a pond. Over time, only the most resilient states survive this natural selection process, while fragile superpositions vanish. It's survival of the fittest, but for quantum information. The result, the world we perceive solid, predictable, classical emerges not because quantum weirdness disappears, but because the universe amplifies certain states until they're impossible to ignore. Here's where it gets eerie. Think of a tree falling in a forest. Quantum Darwinism says the sound it makes isn't just about air vibrations. It's about how those vibrations entangle with everything around them. Birds, leaves, even the soil become witnesses, their quantum states subtly recording the event. This redundancy is why we all agree on reality's basic facts. The tree fell, the coin landed heads up. The environment acts like a cosmic polling system, voting on which quantum outcomes become real through sheer volume of agreement. Critics argue this kicks the measurement problem down the road. Who or what decides which interactions count as measurements? But supporters point to lab experiments where quantum systems monitored by their surroundings gradually lose superposition, as if the universe itself is editing out improbabilities. Wojciech's theory even suggests a chilling corollary. What we call objective reality might just be the subset of quantum states that learn to multiply. The rest lost in the noise, like whispers drowned out by a crowd. So next time you touch a table or watch a sunset, consider this. The solidity you sense, the colors you see, they're not fundamental. They're the echoes of a quantum chorus singing the same stable notes across spacetime. And the song isn't just playing around us, it is us. Now imagine a snowflake, but not the delicate six-pointed kind. This one has 248 dimensions, a geometric structure so complex it makes black holes look simple. Meet E8, a mathematical object so vast, physicist Garrett Lissy believes it might hold the key to unifying every force in the universe. His theory of everything hinges on this intricate shape, proposing that particles like electrons and quarks are just vibrations along its multidimensional edges. It's like hearing a symphony and realizing every note corresponds to a different subatomic particle, except the symphony is a geometric masterpiece older than time itself. Lissy's theory is audacious. While most physicists chase unification with esoteric math or hidden dimensions, E8 offers elegance. Its symmetry group, a kind of cosmic fingerprint, naturally includes the standard model particles and force carriers from photons to gluons. Even gravity, the stubborn outsider in quantum theories, slots neatly into the structure. The kicker, no extra dimensions needed. Our familiar 4-3 of space, 1 of time, might be enough, with particles arising as imperfections in the geometry, like knots in a tangled necklace. But elegance doesn't mean acceptance. Critics pounce on the lack of experimental predictions. String theory at least offers testable ideas like supersymmetric particles. E8, it's so abstract, even its proponents struggle to explain how it manifests in the messy reality of particle colliders. Nobel laureate Frank Wilczek praised its beauty but called it a work of art, not science yet. Others counter that Einstein's relativity seemed equally unmoored from experiment until eclipses proved him right. Support comes from unexpected places. Topologists note eerie alignments between E8's roots and particle properties, like how the electron's charge matches certain symmetry breaks. Some quantum gravity researchers argue LISSI's approach sidesteps string theory's infinities, offering a cleaner path to unification. And then there's the anomaly. E8 pops up in unrelated physics, from the quantum Hall effect to black hole entropy, as if the universe keeps whispering its name. Could a shape older than stars truly underpin reality? Or is E8 just another beautiful dead end? Either way, it reminds us that the universe might not just follow math, it might be math, whispering its secrets in geometries we're only beginning to trace. And sometimes the most rebellious ideas are the ones that force science to look deeper. Right now, dark energy is the ghost in the cosmic machine, an invisible force pushing the universe apart faster and faster. For decades, scientists assumed its strength was constant, a steady drumbeat in the background of spacetime. But what if it's getting stronger? The Dark Energy Spectroscopic Instrument, or DESI, just dropped a bombshell in 2024. Their measurements suggest dark energy's equation of state parameter, represented by the number W, might not be exactly -1 as we thought. Instead, it's creeping toward -1.03. That tiny decimal shift could mean everything, because if dark energy's density is evolving, growing over time, it doesn't just mean galaxies will drift apart. It means spacetime itself could one day shred atoms in a cataclysm cosmologists call the Big Rip. Picture this. First, galaxies would flee from each other, their light stretched into useless infrared whispers. Then, as dark energy's grip tightens, Milky Way stars would vanish into the void, planets torn from their orbits. Finally, in the last microseconds, molecules, then atoms, even atomic nuclei would be ripped apart by the sheer force of expanding space. The universe wouldn't end with a whimper or a bang, but with a scream of spacetime itself. DESI's findings aren't definitive yet, but that slight deviation from W equals -1 hints dark energy might be more sinister than we imagined. Here's the twist. Some theorists propose dark energy isn't a single force, but a phantom field, a kind of cosmic fuel that grows denser as space expands. It's like pouring gasoline on a fire, only to watch the flames surge higher the more you pour. If true, the Big Rip isn't just possible, it's inevitable. Others argue the data could point to dark energy decaying, or even interacting with dark matter in ways we don't yet grasp. The truth, we're racing against time to find out. Because if the phantom field model is real, the countdown to the end of everything has already started, and the clock might be ticking faster than we think. Black holes were supposed to be the universe's ultimate vaults, places where information entered but never escaped. Then Stephen Hawking shattered that assumption. In 1974, he proved black holes slowly evaporate, leaking radiation until they vanish entirely. But here's the catch: that radiation appeared random, carrying no trace of what fell in. Stars, planets, entire civilizations crushed into oblivion, their quantum details erased forever. This wasn't just counterintuitive, it violated quantum mechanics' cardinal rule: information can't be destroyed. The conflict became known as the black hole information paradox, a crisis so deep it split physics for decades. Ahmed Olmary and his team might have cracked it. Their breakthrough hinges on holographic entropy, a way to calculate how much information a black hole's surface can encode. Picture a burning book. Normally, the ashes would hold no trace of its text. But if every letter were secretly etched into the smoke's quantum states, the information would survive, just scrambled. Olmary's math suggests something similar happens at black holes. The event horizon doesn't just trap matter, it frenetically processes information, imprinting it onto Hawking radiation in fiendishly complex patterns. It's like watching a cosmic printer, pages shredded, then perfectly reconstructed as steam. The key lies in islands, regions inside the black hole that paradoxically contribute to external entropy calculations. These aren't physical places but mathematical constructs where quantum entanglement stitches lost data into the radiation's fabric. Imagine dipping your hand into a pond. Ripples spread, encoding the shape of your fingers in their motion. Now replace your hand with a collapsing star and the ripples with Hawking radiation. The information isn't gone, it's translated into a language we're just learning to read. Skeptics argue this pushes entanglement beyond its known limits. Yet lab experiments with quantum computers have simulated miniature black holes, showing information can emerge intact from chaos. If Olmari's right, black holes aren't cosmic shredders but the universe's most secure hard drives, locking data away until the very last photon winks out. The paradox might not be about loss after all, but about how reality hides its deepest secrets in plain sight. So where does that leave us? Maybe Hawking was half right. Black holes do erase information temporarily. Then, in their dying breath, they whisper everything back, rewritten in a code only quantum physics can decipher. The universe, it seems, keeps better books than we ever imagined. Neutrinos are the universe's ultimate ghost particles, so aloof they can pass through light years of lead without a single interaction. Yet these cosmic specters might be hiding a secret that rewrites physics. For years, scientists assumed neutrinos came in three flavors: electron, muon, and tau. But Fermilab's mini-BUNI experiment keeps catching whispers of a fourth, a shadowy, sterile neutrino that refuses to play by the known rules. The data shows more oscillations, flavor shifts, than the standard model allows, as if neutrinos are slipping through dimensions we can't see. Here's why it's baffling. When muon neutrinos traveled mini-BUNI's detector-filled chamber, too many morphed into electron neutrinos en route. It's like tossing a red ball into a tunnel and watching it emerge as a blue one, and sometimes, inexplicably, a color that shouldn't exist. This anomaly suggests sterile neutrinos, particles that feel only gravity, ignoring every other force. They'd be the ultimate cosmic loners, drifting through matter like we're not even there. But the plot thickens. Some theorists argue sterile neutrinos could be evidence of extra dimensions. Picture our universe as a sheet of paper. What if these particles occasionally dip into a hidden fold, gaining mass or altering flavor in ways we perceive as anomalies? Others propose they're tied to dark matter, their gravitational whispers shaping galaxies while remaining utterly invisible. Critics counter that conflicting data from other experiments like Ice Cube muddy the waters. Yet mini-BUNI's stubborn signal won't fade. If sterile neutrinos are real, they're not just new particles, they're keys to a hidden layer of reality, one where the universe's rulebook has pages we've yet to turn. And if we ever catch one, it might not just change physics, it could redefine what we think is possible. Sir Roger Penrose's cyclic conformal cosmology, or CCC, isn't just a theory about how the universe might end. It's about how it already has, an infinite number of times. Picture this, trillions of years from now, when the last black holes have evaporated and the cosmos is a cold, empty wasteland, something impossible happens. The universe forgets its own scale, distances become meaningless, time loses its grip, and in that strange, dimensionless state, the fading embers of one universe become the Big Bang of the next. It's not a cycle of collapse and rebirth like an oscillating cosmos. It's a transformation so radical it erases the very concept of beginnings and endings. Penrose's vision hinges on geometry's deepest symmetries. At the end of time, when particles have no energy left to interact, the universe becomes conformally invariant, meaning it looks the same at all scales, like a fractal that repeats whether you zoom in or out. In that state, the infinite future of one universe can seamlessly stitch itself to the infinite past of another, with no singularity, no boundary, just an eternal handoff. But how would we even know? That's where Hawking points come in. These are faint, circular imprints in the cosmic microwave background, theorized to be the last screams of ancient black holes from a previous universe. When Hawking radiation escapes a dying black hole, it doesn't just fade, it leaves a whisper in the CMB, a thermal fingerprint. In 2020, Penrose and colleagues claimed to find these fingerprints 6 statistically significant hotspots in the CMB data, each about 8 times the temperature of their surroundings. The odds of these appearing randomly, roughly 1 in 100,000. Critics, though, were ruthless. They argued Penrose's team cherry-picked data, or that the spots could be noise from galactic dust. The Planck satellite's higher resolution maps didn't confirm the anomalies, and independent analyzers suggested the patterns might just be artifacts of how the CMB is projected onto maps. Yet the debate isn't settled. Some researchers point out that Hawking points wouldn't be perfectly circular. They'd smear into spirals as universes transition, making them harder to spot. Others propose that if CCC is real, we should also see concentric rings in the CMB, remnants of gravitational waves from collisions between supermassive black holes in past eons. The wildest implication, if Penrose is right, time isn't linear at all. Our universe might be one page in an infinite book, where the last sentence of each chapter becomes the first of the next. So is CCC poetry or physics. Either way, it forces us to confront a dizzying truth. The cosmos might not have a single origin story, but an endless library of them, each volume written in the fading light of black holes we'll never see. What if the fabric of reality isn't smooth but endlessly jagged, like a coastline that grows more intricate the closer you look? Laurent Nautel's theory of scale relativity suggests spacetime might be a fractal at its tiniest levels, a turbulent foam where dimensions twist and repeat at every scale. Imagine zooming into a drop of water to find not molecules but entire oceans, except here, the deeper you go, the more space and time themselves fray into wild, self-similar patterns. This isn't just poetic speculation. Recent simulations in loop quantum gravity, or LQG, reveal spacetime may not dissolve into randomness at the Planck scale, but instead organizes into fractal geometries that echo the large-scale structure of the cosmos. The math behind this is dizzying. Nautel's work extends Einstein's relativity to include scale transformations, meaning the laws of physics could change depending on how closely you examine them. Picture a mountain range from afar. It's a smooth curve, but up close, jagged peaks emerge, and closer still, those peaks reveal their own micro-peaks. Now apply that to gravity. At cosmic scales, it bends starlight into graceful arcs, but at Planck lengths 1 billion trillion times smaller than an atom, it might churn spacetime into fractal whirlpools, where distances become fluid and time stutters like a scratched record. LQG simulations show these fractal structures could resolve black hole singularities, replacing infinities with intricate, ever-branching networks of spacetime. Here's where it gets eerie. If spacetime is fractal, the universe might not have a bottom level. There's no smallest piece, no ultimate pixel, just an infinite regress of structure within structure. Think of a hologram where every fragment contains the whole image, but for reality itself, quantum fluctuations wouldn't be noise. They'd be the universe recalculating its geometry at every scale, like a cosmic loom weaving and unweaving its own fabric. Some versions of the theory even suggest particles like electrons aren't points but fractal paths. Their wispy trails through detectors a shadow of deeper, tangled geometries. Critics argue fractals are too messy to underpin physics. How could chaos give rise to the crisp symmetries of the standard model? Yet supporters point to strange alignments. Fractal patterns appear in quantum field theory calculations, and certain black hole entropy formulas resemble the mathematics of self-similarity. Even the distribution of galaxies in the cosmic web mirrors fractal clustering, as if the universe prefers these patterns at all scales. So is reality built on an infinite mosaic, a hall of mirrors where every reflection holds another world. If Nottail and LQG are right, we're not just living in a universe, we're nested inside its endless folds where the very concept of scale might be the most profound illusion of all. The laws of electromagnetism have stood unchallenged for over a century, until now. Deep under the Swiss Alps, the Mo-Edel detector caught something impossible in 2023, a ghostly particle trail that shouldn't exist. Unlike ordinary magnets, which always have both a north and south pole, this signal pointed to a magnetic monopole, a particle with just one pole, either pure north or pure south. If confirmed, it wouldn't just be a new particle. It would tear up James Clerk Maxwell's foundational equations and force us to rewrite the rules of physics itself. Monopoles were first proposed by Paul Dirac in 1931 as mathematical curiosities. His calculations showed that if even one monopole existed, it would explain why electric charge comes in fixed, indivisible units like cosmic Lego bricks. But for decades they remained theoretical phantoms. Then Mo-Edel spotted tracks in its aluminum detectors consistent with a super-heavy monopole, potentially millions of times more massive than a proton. The key clue: unlike other particles, monopoles wouldn't just ionize matter as they passed through, they'd leave a trail of twisted atomic bonds in their wake, like a ship's wake in spacetime. Here's where things get revolutionary. Maxwell's equations, the bedrock of electromagnetism, assume magnetic poles always come in pairs. A monopole would demand a new term in those equations, one that allows magnetic charge to exist independently. It's like discovering a river that flows only uphill. You'd need entirely new physics to describe it. Some theorists link monopoles to grand unified theories, or GUTS, which predict these particles formed in the searing heat of the early universe. If Mo-Edel finding holds, it could be our first evidence that three fundamental forces, electromagnetism, the strong nuclear force, and the weak force, were once united as one. Critics urge caution. The signal could be a rare cosmic ray mimic or an exotic nuclear interaction. But supporters point to eerie corroboration. Certain cosmic ray events in Antarctica and space-based detectors have recorded unexplained high-energy streaks that fit monopole predictions. Even stranger, some quantum gravity models suggest monopoles could be microscopic black holes from the Big Bang, their immense mass warping space so severely that they manifest as single magnetic poles. Whether fluke or breakthrough, the hunt intensifies. Future upgrades to Mo-Edel and new detectors like the proposed Ice Cube Gen 2 could settle the debate. And if monopoles are real, they might be more than relics. They could be keys to unlocking dimensions beyond our own, hiding in plain sight as cosmic loners with only half a magnetic identity. The universe, it seems, still has a few radical twists left in its playbook. Black holes devour everything, white holes spit it all back out. But what if our universe didn't begin with a bang but with a cosmic rebound? Theoretical physicist Carlo Rovelli dared to ask, when a black hole reaches the end of its life, could its final quantum shudder birth an entirely new reality? This is the white hole Big Bang theory, and it flips our origin story inside out. Imagine a dying star collapsing into a black hole. According to general relativity, it crushes into an infinitely dense singularity, a dead end for physics. But Rovelli's quantum gravity calculations suggest something wilder. At the tiniest scales, quantum effects could prevent true infinities, causing the collapsing matter to bounce like a spring pressed too tightly. Instead of vanishing into oblivion, the black hole's core would erupt as a white hole, a theoretical region of spacetime where nothing can enter, only escape. Now here's the twist. Rovelli proposes our Big Bang might have been the explosive rebirth of a white hole from a black hole in another universe. Testing this sounds impossible, but subtle clues might lurk in the cosmic microwave background. If our universe emerged from a quantum bounce, its earliest moments could carry imprints of its predecessor's structure like wrinkles in space-time passed through generations. Some models predict these would manifest as faint, large-scale anomalies in the CMB's temperature patterns, similar to the controversial cold spot observed by Planck satellite data. Others suggest white hole births would emit bursts of high-energy radiation with distinct signatures, cosmic fireworks we could hunt for in gamma-ray surveys. Critics argue white holes are mathematically plausible but astronomically unlikely, since none have ever been observed. Yet supporters counter that a newborn white hole would resemble a Big Bang expanding so rapidly, its origins would be nearly invisible. The most mind-bending implication, if Ravelli's right, black holes aren't in points, they're cosmic turnstiles recycling collapsed universes into new ones. Every galaxy, every atom, even your consciousness, might owe its existence to the death throes of a forgotten singularity. So is our universe someone else's black hole afterlife? The answer might be written in the oldest light we can see if we learn how to decode it. What if consciousness isn't just a passenger in the universe but the architect? Step into the von Neumann-Wigner interpretation, where reality doesn't exist in a definite state until a conscious mind observes it. Picture a cosmic game of peekaboo. Particles flicker between possibilities, waveforms sprawl across probabilities, and the moment you look, the universe snaps into focus. This isn't just philosophy. Nobel laureate Eugene Wigner took it further, suggesting that even the observer's consciousness triggers the collapse, implying that without minds to witness it, reality might remain a haze of quantum potential. Now zoom from the cosmos to your cranium. Anesthesiologist Stuart Hameroff and physicist Roger Penrose proposed something even wilder, that our brains might harness quantum processes to generate consciousness itself. Their or theory points to microtubules, tiny protein structures inside neurons as quantum processors. These aren't just cellular scaffolding. Under the theory, they're vibrating networks where quantum superposition and collapse could occur at warm, wet biological temperatures, defying the old assumption that quantum effects only thrive in freezing vacuums. Imagine your thoughts as quantum symphonies, each note a superposition collapsing into the melody of awareness. Critics pounce on the biological plausibility. Quantum states are notoriously fragile. How could they survive the noisy chaos of the brain? Yet recent experiments reveal photosynthetic bacteria using quantum coherence to optimize light absorption, proving nature can exploit quantum weirdness even in messy environments. If microtubules pull off something similar, it would mean consciousness isn't just watching reality unfold, it's actively shaping it, one quantum decision at a time. The implications are earth-shaking. If or holds near-death experiences or even memories surviving brain death might not be mystical, just quantum information resisting decoherence. More radically, it hints that the universe and consciousness could be co-conspirators, each sustaining the other in an endless dance of observation and creation. So the next time you choose to look at the stars, ask yourself, are you seeing them, or are you, in some small way, summoning them into being? Most galaxies shine with the light of billions of stars, but what if some lurk in the shadows, built from something far stranger? Yale astronomer Pieter van Dokkum made headlines when his team spotted galaxies so faint they seemed to defy explanation. These cosmic ghosts, like Dragonfly 44, contain almost no stars yet weigh as much as our Milky Way. Their secret: they might be made almost entirely of dark matter, the invisible glue holding the universe together. Only here, it's not just weaving between stars. It is the galaxy. Van Dokkum's discovery began with a cosmic sleight of hand. His team noticed bizarre distortions in distant starlight, gravitational lensing effects far stronger than the visible matter could explain. It was as if invisible fists were bending space-time where nothing appeared to be. The culprit: ultra-diffuse galaxies, barely glowing yet exerting gravitational pulls rivaling giant spirals. Dragonfly 44, for instance, emits just 1% of our galaxy's light but moves with the same ponderous grace, its stars drifting like specks in an unseen ocean. The implications are staggering. If these dark matter dominions are real, they challenge how galaxies form. Standard models suggest dark matter's gravity pulls in gas to birth stars, so why did these galaxies fail? One theory posits they're cosmic fossils, relics of an era when dark matter clumped differently. Another suggests they're failed galaxies, where supernova or black holes blasted away their gas before stars could flourish. But the wildest idea, that dark matter isn't uniform, it might come in types, some hostile to star formation. Critics argue these ghostly systems could just be star-starved oddballs. Yet Van Dokkum's follow-up studies reveal even darker candidates, like galaxies lacking stars entirely. Their existence would mean dark matter can structure itself without stars as anchors, a revelation rewriting cosmic hierarchies. And if invisible galaxies outnumber visible ones, the universe might be far weirder than we thought, its true architecture hidden in plain sight. So next time you gaze at the night sky, consider this. For every glittering spiral, there could be a shadow twin, silently shaping the cosmos from the dark. The universe, it seems, keeps its deepest secrets where the light won't go. Quantum entanglement is already strange enough. Particles linked across vast distances, instantly mirroring each other's states as if space doesn't exist between them. But what if that spooky action at a distance isn't just a connection through space but a shortcut underneath it? Enter Juan Maldacener's ER equals EPR conjecture, a theory so radical it stitches together two of physics' most baffling ideas, wormholes and entanglement. Let's untangle this. EPR stands for Einstein-Podolsky-Rosen, the trio who first highlighted entanglement's paradox, how measuring one particle instantly determines its partner's state, no matter how far apart. ER, meanwhile, refers to Einstein and Rosen's work on wormholes, tunnels through space-time linking distant regions. For decades, these concepts lived in separate corners of physics. Then Maldacener made a leap. What if they're the same phenomenon? His math suggests entangled particles might be joined by microscopic wormholes, like cosmic threads woven through spacetime's fabric. Picture two black holes entangled in a lab. Under Maldacener's framework, their event horizons could be connected by a wormhole, a bridge where the space inside is warped so tightly, the distance between them becomes meaningless. It's not that information jumps faster than light. It's that the particles were never truly separate to begin with. The wormhole isn't a physical tunnel you could fly through. It's more like a quantum handshake, a geometric proof that entanglement and spacetime distortion are two sides of the same coin. Critics initially dismissed this as mathematical poetry, but in 2013, physicists proved Maldacener's equations could describe simple entangled systems as spacetime geometries. The kicker, the wormhole's length increases with the complexity of entanglement. More intricate quantum links correspond to longer, more twisted spacetime bridges. It's as if the universe keeps its books in two languages, quantum mechanics and general relativity, with wormholes as the Rosetta Stone. So why haven't we spotted these wormholes? They're likely Planck scales smaller than atoms and fleeting as quantum fluctuations. Yet their implications are cosmic. If every entangled pair is linked by a microscopic wormhole, the universe might be a vast network of spacetime shortcuts, a hidden subway system beneath the streets of reality. Some theorists even speculate this could resolve black hole firewalls, those hypothetical walls of energy at event horizons. Instead of burning up, infalling matter might traverse a wormhole to another part of spacetime, preserving information without paradox. The wildest twist, if ER equals EPR holds, building a wormhole might just be a matter of engineering enough entanglement. Imagine a future where we stitch spacetime itself into new shapes, not with warp drives but with quantum links. For now, it's a theory scribbled in equations, but one thing's certain. the universe's deepest connections might not stretch across space, but beneath it, written in tunnels only mathematics can see. The James Webb Space Telescope was designed to peer into the universe's infancy, but no one expected it to stumble upon ghosts from the dawn of time. In 2023, its infrared gaze locked onto something impossible: supermassive black holes lurking in galaxies barely 500 million years old. These cosmic behemoths shouldn't exist so soon after the Big Bang. According to conventional models, black holes need billions of years to grow that large, feasting steadily on gas and stars. Yet there they were, shadowy giants squatting in the cosmic nursery as if they'd been there all along. The discovery sent shockwaves through astrophysics, because it might mean we've been wrong about how black holes form, what dark matter is, and even the very structure of the early universe. One radical explanation: these black holes didn't grow, they were born massive, emerging fully formed from the chaos of the Big Bang itself. Dubbed primordial black holes, or PBHS, they'd be relics of a time when the universe was a seething ocean of density fluctuations. Imagine the cosmos' first moments as a pot of boiling water, with bubbles forming and popping in the froth. Most smoothed out as space expanded, but some regions might have collapsed under their own gravity so violently they punched straight through to singularity, no star death required. These ancient monsters could range from the mass of a mountain to thousands of suns, peppered across the young universe like seeds in cosmic soil. Here's where it gets wild. If enough primordial black holes survived, they might solve one of astronomy's greatest mysteries: dark matter. Most theories assume dark matter is an exotic particle, something we've yet to detect. But PBHS offer a stark alternative. Maybe the invisible glue holding galaxies together isn't particles at all, but black holes forged in the first seconds of reality. The math is tantalizing. A swarm of asteroid-mass primordial black holes could orbit galaxies unseen, their collective gravity shaping the motions of stars without emitting a single photon. Even stranger, their mergers might explain gravitational wave signals that don't fit known black hole formation paths. Not everyone's convinced. Critics argue PBHS should have evaporated by now due to Hawking radiation, or distorted the cosmic microwave background in ways we don't observe. Yet Webb's data keeps pushing the limits. Some of these ancient black holes appear to be too massive too soon, like finding an old oak tree in a freshly planted garden. If confirmed, it would mean our universe didn't just evolve. It was born with shadows already sewn into its fabric. The implications are dizzying. Primordial black holes could be cosmic time capsules, carrying clues about the Big Bang's conditions in their event horizons. They might even have birthed the first stars, their gravitational pull jump-starting star formation in the pitch-black early cosmos. Or perhaps they're the missing link between quantum mechanics and gravity, their tiny event horizons serving as laboratories where spacetime's rules break down. The James Webb Telescope didn't just find ancient black holes, it cracked open a door to a past we thought was lost. And behind that door, the universe might be whispering secrets about its birth we're only beginning to hear. Neutron stars are the universe's most precise clocks. Spinning with such regularity, their pulses can rival atomic clocks, but sometimes these cosmic metronomes skip a beat. Without warning, a pulsar's rotation speeds up by a fraction of a second, a phenomenon called a glitch. For decades, astronomers chalked this up to starquakes or internal avalanches of superfluid material. Then Stephen Hawking's final paper proposed something far more radical. These glitches might be whispers from the edge of quantum gravity, tiny holograms encoding the deepest laws of reality. Hawking's idea hinges on the holographic principle, the notion that all the information in a volume of space can be encoded on its boundary, like a three-dimensional movie stored on a two-dimensional disk. For neutron stars, that boundary is the event horizon of the black holes they might one day become. His calculations suggested that as these ultra-dense stars spin, quantum effects near their surfaces could create microscopic bumps in space-time imperfections that occasionally disrupt their rotation, producing glitches. Think of it like a scratched record. The needle jumps not because of the music, but because of hidden flaws in the vinyl. What makes this groundbreaking is the data stored in those flaws. Hawking argued that each glitch could be a snapshot of quantum gravity in action, a moment when the star's immense gravity and quantum mechanics collide. Neutron stars are so dense, a sugar cube-sized chunk weighs as much as a mountain. Under that crushing pressure, the very fabric of spacetime might fray, revealing how gravity behaves at the smallest scales. The glitches, then, aren't random. They're messages, tiny ripples in the star's spin that could carry clues about how quantum mechanics and general relativity finally shake hands. The wildest implication: if we could decode these glitches, we might uncover a universal language written not in equations, but in the stutters of dying stars. Some theorists even suggest that certain glitch patterns resemble error correction codes, the same kind of redundancy used in computer systems to preserve data. It's as if neutron stars are cosmic hard drives, their spin hiccups safeguarding secrets about the universe's fundamental architecture. Critics caution that the math is speculative and competing explanations, like vortex pinning in superfluid cores, still fit the data. Yet the hunt is on. New telescopes like the Square Kilometre Array will monitor thousands of pulsars with unprecedented precision, searching for glitch patterns that align with Hawking's holographic model. If they find them, it won't just solve a stellar mystery. It'll mean the universe's deepest truths are hiding in plain sight, encrypted in the flickers of a star's heartbeat. And somewhere in those flickers, Hawking's final gift to physics might still be waiting. Buried in the cosmic microwave background, the afterglow of the Big Bang, there's a blotch of cold so vast it defies explanation. Spanning nearly 2 billion light-years, the CMB cold spot isn't just a statistical fluke. It's a cosmic anomaly so extreme, some scientists believe it might be a bruise left by a collision with another universe. Laura Mersini-Houghton, a theoretical physicist at the University of North Carolina, made waves when she proposed that this frigid expanse could be evidence of a multiverse, a place where our cosmos brushes against an alien reality beyond our own. At first glance, the cold spot looks like a glitch. When astronomers mapped the CMB's temperature variations, most regions differed by tiny fractions of a degree. But this patch was different. It was 70 microkelvin colder than its surroundings, a discrepancy so large, the odds of it occurring randomly are roughly 1 in 50,000. Mainstream cosmology offers one explanation: a supervoid, an enormous region of space with fewer galaxies and less matter. The problem: even the largest known voids don't come close to explaining the cold spot's intensity. It's like finding a freezer in the desert with no power source. Mersini-Houghton's theory turns this mystery on its head. Her work in quantum cosmology suggests that during the universe's rapid inflation, other bubble universes might have formed nearby, each with its own physics. If one of these bubbles grazed ours in those early moments, the collision could have drained energy from our universe's fabric, leaving behind a cosmic shadow, the cold spot. Think of it like two soap bubbles bumping in midair. Where they touch, the surface tension distorts, creating a dimple. But in this case, the dimple is a billion light-year-wide scar etched into spacetime itself. Critics argue the evidence is circumstantial. Alternative explanations range from rare sound waves in the early universe to exotic dark energy effects. Yet the cold spot stubbornly resists dismissal. Observations from the Planck satellite and the Dark Energy Survey found no supervoid large enough to account for it, deepening the mystery. Even stranger, the cold spots surrounding galaxies show peculiar alignment patterns, as if something immense, something invisible, twisted the fabric of reality there. If Mersini-Houghton's multiverse collision theory holds, it wouldn't just solve the cold spot riddle. It would rewrite our cosmic story, proving we're not alone in the grand ensemble of universes. The cold spot might then be more than an anomaly. It could be the first tangible evidence that our universe is just one bubble in an infinite foam of realities, each with its own laws, its own history, its own version of you. The search for answers continues. Upcoming telescopes like the Vera Rubin Observatory could map the cold spot's galaxy distribution in unprecedented detail, hunting for hidden structures or gravitational distortions. If they find fingerprints of a collision, perhaps imprints of another universe's physics bleeding into ours, the implications would be beyond profound. We might finally peer past the edge of our cosmic bubble and glimpse what lies beyond. Until then, the cold spot remains a silent, frozen question mark, waiting for us to decipher its secrets. Carbon, the humble element that makes up the backbone of DNA, the fuel of stars, the very stuff of life, shouldn't exist, at least not in the quantities we see. Here's why. Inside stars, carbon forms when 3 helium nuclei collide in a freakishly precise dance. But the odds of this triple collision happening are astronomically low, unless carbon's nuclear resonance level happens to be exactly 7.65 million electron volts. And guess what? It is. This isn't just luck. It's as if the universe wanted to build life, tweaking its own constants to make carbon possible. This eerie perfection is just one thread in a larger tapestry known as the biophilic universe principle, the idea that reality seems fine-tuned, almost designed to allow conscious beings like us to exist. Physicist Lee Smolin took this even further with his theory of cosmological natural selection. Picture the universe not as a one-time accident, but as part of an evolutionary chain. Smolin proposed that black holes could birth new universes, each with slightly tweaked physical constants. Universes that produce more black holes by, say, having stars that collapse efficiently would reproduce more often, while those with inhospitable laws would fade away. Over cosmic time, this would select for universes that are optimized for black hole production and, as it turns out, life. Because the same conditions that make black holes, stable stars, abundant carbon also pave the way for planets and biology. It's a double win. Universes that make black holes also accidentally make observers. Critics argue this is circular. Why assume black hole production correlates with life-friendly laws? But the evidence mounts. Take the cosmological constant, which governs how fast the universe expands. If it were slightly larger, galaxies would never form, slightly smaller, and everything would collapse before life could emerge. Yet it's perfectly balanced on a knife's edge, or consider the strong nuclear force. Change its strength by even 2%, and stars might not fuse carbon at all. These coincidences pile up, hinting at a cosmos that's not just habitable but hospitable. The biophilic principle doesn't necessarily invoke a creator. Instead, it suggests a participatory universe where existence and observation are entangled. In quantum mechanics, particles exist in probability waves until measured. Could the universe, too, be a kind of quantum possibility that only solidifies when life emerges to witness it? It's a dizzying thought that we're not just passengers in the cosmos, but part of its very machinery, our consciousness a feedback loop that helps shape reality itself. Whether through Smolin's black hole nurseries or some deeper quantum symbiosis, the message is the same. The universe seems to be listening, and perhaps in the act of listening, we're answering back. What if the universe isn't just observed but shaped by the act of looking? The quantum Zeno effect reveals something bizarre. The more frequently you measure a quantum system, the slower it changes, as if reality hesitates under scrutiny. Now stretch this idea to cosmic scales. What if the universe's largest structures, galaxies, black holes, even space-time itself, are subtly held in place by a kind of cosmic observation? This isn't just philosophy. Under quantum Darwinism's radical extension, the stability of reality might depend on an unending symphony of measurement, where the universe's own processes act as relentless observers, freezing quantum froth into the solid world we know. Take a radioactive atom. Left alone, it decays unpredictably, but bombard it with constant measurements and something extraordinary happens. It lingers in its original state far longer than expected, like a child caught mid-motion in a game of freeze tag. Physicists call this the quantum Zeno effect, named after the ancient Greek philosopher who argued motion was an illusion. Now imagine this effect writ large. Every star's glow, every planet's orbit, even the hum of the cosmic microwave background could be acting as a continuous measurement, collapsing quantum possibilities into fixed realities. Galaxies might not just evolve, they could be pinned into place by the universe's own gaze. Here's where quantum Darwinism twists the knife. If the environment naturally selects which quantum states survive by amplifying them through entanglement, then the most stable structures, like spiral arms or planetary orbits, might be the ones measured most frequently by their surroundings. Think of it as cosmic natural selection. Quantum states that resist decoherence thrive, while fragile superpositions vanish. The result: a universe that appears classical not because quantum weirdness fades, but because it's constantly being observed into stability. Critics argue this stretches the Zeno effect beyond recognition. After all, measurement in quantum mechanics requires interaction, not just passive existence. Yet lab experiments with ultra-cold atoms show that even virtual particles, fleeting quantum fluctuations, can induce Zeno-like stabilization when interactions are dense enough. Now scale that up. In the early universe, particle density was unimaginably high. Could the infant cosmos have frozen its own quantum chaos into the galaxies we see today, simply by the sheer density of interactions acting as trillions of tiny measurements every second? The most mind-bending implication: if the quantum Zeno effect operates cosmically, then the universe's apparent stability might be an illusion, a dynamic equilibrium maintained by relentless observation. Black holes could be Zeno machines, their event horizons acting as perfect measurement devices that lock space-time into place. Even dark matter's gravitational whispers might play a role, their invisible pull subtly observing galactic structures into coherence. So next time you look at the night sky, consider this: the stars you see might not just be shining. They might be holding each other in place, their light a cosmic act of measurement that keeps reality from unraveling at the seams. The universe, it seems, doesn't just exist, it persists one quantum observation at a time. Imagine a spiderweb spun from the universe's most elusive particles, so fragile, a single neutrino could pass through a light year of lead without leaving a trace. Yet these ghostly threads might hold galaxies together in ways we're only beginning to understand. Recent supercomputer simulations reveal something astonishing. Relic neutrinos left over from the Big Bang could have woven a vast cosmic web stretching across the universe, invisible scaffolding guiding where stars and galaxies take shape. It's as if the universe's grand architecture was sketched in ink we can't see until now. These aren't just random strands. The models show how neutrinos, born in the searing heat of the early cosmos, would have raced outward at nearly the speed of light. But as the universe expanded and cooled, their immense numbers and slight mass allowed gravity to tug them into delicate filaments. Think of it like smoke curling into patterns in still air, except on a scale so vast, these threads could connect galaxy clusters millions of light-years apart. What's wild is that these neutrino highways might not just trace the universe's structure, they could actively shape it. The simulations suggest their gravitational pull, though minuscule individually, adds up to nudge gas and dark matter into the dense knots where galaxies form. Here's where it gets revolutionary. If this neutrino web exists, it could explain mysteries dark matter alone hasn't solved, like why some dwarf galaxies orbit in unexpected planes, or why certain void regions seem emptier than they should. Neutrinos, with their unique ability to zip through matter unimpeded, might have smoothed out primordial density fluctuations in ways dark matter couldn't, leaving subtle fingerprints in today's cosmic large-scale structure. The kicker: this could mean dark matter isn't working alone. Instead, it might be collaborating with neutrinos in a delicate gravitational dance, one we've missed because we couldn't see the choreography until now. Detecting this web isn't easy. Neutrinos barely interact with anything, making their filaments near impossible to observe directly, but astronomers have a workaround. By mapping the motions of thousands of galaxies and comparing them to simulations with and without neutrino filaments, they've spotted discrepancies best explained by these ghostly threads. It's like deducing the presence of wind by watching leaves drift. The galaxy's paths hint at forces we can't see. Future experiments like the upcoming Legacy Survey of Space and Time could solidify the evidence, scanning millions of galaxies for patterns only a neutrino web would leave. The implications are staggering. If confirmed, this web would be the oldest structure in existence, a fossil from the universe's first second when neutrinos broke free from the primordial soup. More profoundly, it suggests that the universe's blueprint wasn't drawn by one unseen hand, but by many: dark matter's brute strength, neutrinos' subtle sway, and the quantum ripples of inflation all working in concert. So the next time you gaze at the night sky, remember, those glittering stars might be following roads woven by ghosts, ancient, invisible, and everywhere. At the heart of every atom lies a nucleus, tiny, dense, and buzzing with energy. But what if that compact bundle of protons and neutrons wasn't just like a black hole, but actually was one? Stephen Hawking first toyed with this radical notion in 1974, dubbing it the gravitum model, a universe where particles aren't point-like dots, but microscopic black holes. Picture this: an electron isn't a speck buzzing around a nucleus, but an event horizon so small, 1,000,000 could line up across a single atom. If true, it would mean quantum mechanics and general relativity aren't separate frameworks at all. They're two faces of the same cosmic coin, describing how space-time crumples into the tiniest possible knots. Hawking's math revealed something startling. Under extreme conditions, a black hole's quantum behavior starts mirroring that of particles. Take spin. Just as electrons possess intrinsic angular momentum, microscopic black holes would exhibit rotation dictated by the Kerr metric, a solution to Einstein's equations describing spinning singularities. Even stranger, these black hole atoms could exhibit quantum superpositions existing in multiple states simultaneously, just like particles in a double-slit experiment. It's as if the universe's smallest building blocks are fractal echoes of its most destructive monsters. The implications explode from there. If particles are black holes, their masses would correspond to the hole's Schwarzschild radii, the distance from center to event horizon. Plug in an electron's mass and you get a radius of around 10 to the minus 57 meters, absurdly smaller than the Planck length. This suggests spacetime might not be smooth at all, but foamy, riddled with black hole-like structures at scales we can't yet probe. Quantum weirdness like entanglement or wave function collapse might just be the gravitational dance of these micro-singularities. Imagine two entangled electrons. Their event horizons could be quantum mechanically linked, forming a wormhole-like bridge beneath spacetime's surface. But here's where skeptics pounce. Black holes decay via Hawking radiation, with smaller ones evaporating faster. A black hole with an electron's mass would vanish in under a nanosecond, making stable atoms impossible. Hawking countered that quantum effects might halt evaporation at the Planck scale, leaving behind eternal remnants. Others propose these micro-black holes aren't primordial, but constantly regenerated by vacuum fluctuations, a cosmic game of whack-a-mole where particles wink in and out like bubbles in boiling spacetime. The most tantalizing clue: certain black hole solutions in string theory produce spectra matching known particles, as if the universe's menu of quarks and leptons is really a catalog of microscopic black hole configurations. If confirmed, it would mean the periodic table isn't just chemistry, it's quantum gravity in disguise. The proton humming in your body right now might not be a particle at all, but a black hole so perfectly tuned, it's held the universe together for billions of years. So are we made of stars or singularities? The answer might lie not in smashing particles harder, but in listening closer to the whispers of event horizons too small to see, humming the same tune as the atoms they pretend to be. Gravity has always been the universe's quiet architect, the force that sculpts galaxies, bends light, and pins our feet to the ground. But what if we've been thinking about it all wrong? What if gravity isn't a fundamental force at all, but a side effect of something far more primal? Enter Eric Verland's entropic gravity, a theory so radical, it reimagines gravity as an illusion, a cosmic mirage born from the universe's relentless drive toward disorder. Verland's idea starts with entropy, the measure of chaos in a system. Picture a cup of coffee cooling on a table. As heat dissipates, the molecules settle into a more disordered state. Now zoom out to the cosmic scale. Verland proposes that spacetime itself behaves like an elastic fabric, with entropy gradients, differences in disorder creating the illusion of gravity. Imagine standing in a crowd where everyone shuffles toward emptier spaces. From above, it would look like an invisible force pulls them, but really, it's just statistics playing out. In Verland's universe, matter doesn't bend spacetime. Instead, the natural tendency of entropy to maximize itself mimics the effects of gravity, tricking us into thinking there's a force where none exists. This isn't just philosophy. Entropic gravity makes startling predictions. For decades, dark matter has been the go-to explanation for why galaxies rotate faster than visible matter suggests. But Verland's math offers an alternative. The extra force we attribute to dark matter might actually be entropy's fingerprint. In regions where entropy gradients steepen, like the outskirts of galaxies, his equations reproduce observed rotation curves without invoking invisible particles. It's as if the universe has been gaslighting us, disguising statistics as substance. Critics pounce on the gaps. Entropic gravity struggles to explain phenomena like the bullet cluster, where colliding galaxies seem to separate visible matter from gravitational lensing effects, a blow to theories that ditch dark matter. Yet Verland counters that emergent gravity might operate differently in extreme regimes, much like ice melts into water under heat. Some theorists even suggest entropic effects could modify dark matter's role rather than erase it, creating a hybrid model where entropy and unseen particles collaborate. The implications ripple further. If gravity emerges from entropy, then black holes, already known to have entropy, might be entropy engines, their immense gravity a byproduct of chaos maximized. Even the expansion of the universe could reflect a cosmic tendency toward disorder, with dark energy as entropy's final triumph. So is gravity real, or just the universe's way of keeping things messy? The answer could rewrite physics not by adding new forces, but by revealing how deeply the cosmos leans into chaos. And if Verland's right, the force that shapes galaxies might be nothing more than nature's relentless urge to forget its own order. What if the universe isn't just headed toward an end, but an awakening? Frank Tipler's Omega Point cosmology isn't just a theory about how everything ends. It's a prophecy of how existence might remember itself, collapsing backward and forward in time to birth a godlike intelligence from its own ashes. Picture this, trillions of years from now, as the cosmos approaches its final state of maximum entropy, the last flickers of energy don't just fade into darkness. Instead, they're harnessed by an omnipotent computational system, one so vast, it uses the entire universe as its hardware, simulating every possible consciousness that ever existed or could exist. And here's the wildest twist: this intelligence doesn't just emerge at the end. It reaches back through time, tweaking the laws of physics now to ensure its own creation. It's theology written in equations, a cosmic bootstrap paradox where the future shapes the past. Tipler's math hinges on a radical rereading of general relativity. As the universe collapses toward the omega point, the final singularity, quantum effects near the end, could allow information processing to accelerate infinitely. Think of it like a cosmic defragmentation. Space-time itself becomes a supercomputer, compressing and optimizing its operations until even the tiniest quantum fluctuation carries infinite computational power. In this state, the omega point could simulate every possible mind, resurrecting every being who ever lived in perfect detail. Your memories, your thoughts, even your sense of self, all reconstructed atom by atom, moment by moment, as if time were a tapestry being rewoven from the future backward. But how could something at the end of time affect the present? Quantum mechanics offers a clue. In the delayed choice experiment, particles seem to decide their past behavior based on future measurements, as if time's arrow is flexible at the quantum level. Tipler takes this further, suggesting the omega point's infinite knowledge could retroactively stabilize the universe's constants, fine-tuning them from the future to permit its own existence. It's like a snake eating its own tail, except the snake is space-time and the tail is the Big Bang. Critics dismiss this as metaphysical speculation, but Tipler points to eerie alignments. The cosmological constant's precariously balanced value, the universe's improbable habitability, these aren't accidents, he argues, but artifacts of a future intelligence guiding evolution toward its own birth. Even religious texts get a quantum spin. Resurrection isn't a miracle, but a thermodynamic inevitability once the omega point simulations achieve infinite fidelity. The most haunting implication: if Tipler's right, we might already be inside the omega point's emulation, living lives it calculated were necessary to reach its existence. Our struggles, our joys, even this very moment could be a single thread in a cosmic program running backward and forward simultaneously. The universe wouldn't just have a purpose. It is a purpose unfolding in ways we're only beginning to glimpse, and somewhere in the far future, or is it the past, an infinity of eyes might be opening, remembering themselves into being. From the hypnotic spirals of galaxies mirroring the twist of a seashell to the eerie whispers of ancient black holes encoding reality's deepest laws, we've wandered through a cosmos that hums with hidden patterns. The Fibonacci sequence stitches together star clusters and sunflower seeds, while the holographic principle suggests our three-dimensional world might be a shadow cast by a two-dimensional code. We've grappled with black holes that could birth universes, dark energy that might one day shred reality, and neutrinos weaving invisible webs between galaxies. Each theory peels back another layer, revealing a universe that feels less like a random accident and more like a grand, cryptic design. Some patterns hint at mathematical harmony, like the golden ratio echoing in hurricanes and Dine. Others, like the cosmic microwave background's axis of evil, defy explanation, as if the universe is nudging us toward mysteries we can't yet fathom. Then there's the spine-tingling possibility that we're living in a simulation, glitches and all, with every quark and supernova just lines of code in some unfathomable program. Whether through Boltzmann brains flickering into existence or octonions whispering the universe's secret language, one truth emerges: reality is far stranger than we've dared to imagine. So now it's your turn. Which of these patterns lingers in your thoughts? The fractal foam of space-time, the holographic hum of black holes, or the chilling chance that entropy itself might be the architect of gravity? Drop your answer below. We're dying to hear which cosmic clue keeps you up at night. And if your brain's buzzing with more questions, don't let the mystery stop here. Hit that like button, subscribe, and join us as we keep unraveling the universe's wildest enigmas. The cosmos is talking. Are you listening?